I want you to try and step back in time with me to 1947. Picture it. There's no big explosion, no huge spectacle. Instead, you're just looking at a lab bench at Bell Labs, and on it there's this chunk of dull gray germanium. It's maybe the size of your thumbnail. And it's got a few gold contacts pressed into it. That was it. That was the first point contact transistor. And it's this quiet, almost invisible starting pistol for a race that, well, it completely rewired the entire planet. At the conceptual center of this whole seismic shift was one man, William Shockley. He didn't just, invent a device. He figured out how to program matter. So our mission today is to do a deep dive into the foundational physics of his invention. Specifically, we're going to look at how he learned to control the very flow of energy and information, the structured movement of particles, and we're going to view it all through the pretty radical lens of motion theory, or MT.
That's right. And it's a powerful lens. When you look at Shockley's work through MT, you see he essentially turned a passive crystalline solid into this dynamic system of programmable motion channels. He created a mechanism for a solid object to reliably block or allow or even redirect energy flows, and all based on these tiny, tiny external control signals. And the real utility of MT here comes from how it defines entropy as. We don't just see it as, simple disorder. We define it as having two key components. There's SLEETH, which is thermal entropy. That's the noisy, random, chaotic heat. And then there's SCO, coherent entropy, which is the structured, ordered motion that we actually call a signal. Shockley's entire genius, really, was about minimizing that first one, the noise, while maximizing control over the second one, the signal.
So if we picture Shockley as like the ultimate motion traffic engineer, you have to contrast the materials he had.
Right.
You have traditional metals, they have incredible conductivity. It's this dense, free sea of electrons just moving everywhere, which is great for transmitting power, but it's terrible for control. You can't just easily turn that flow off or divert it with any precision.
Exactly. A metal is like a 6-lane highway with no traffic lights, no exits, just pure flow. Semiconductors, though, they offer a much sparser and, crucially, a tunable electron sea. The MT thesis here is that Shockley found a way to carve these highly specialized motion lanes right into the crystal. This ensures that a small, structured control signal, an input of SCO, could reliably gate a much larger, often noisier supply flow. The control is literally built into the structure of the material.
Okay, let's unpack that internal structure, because it really all starts at the atomic level, doesn't it? I mean, I get the basics of quantum physics, but how does this crystal lattice actually function as a kind of an energy map for structured movement?
Yeah. Well, we see the crystal lattice as a standing wave scaffold. It's a scaffold of atomic vibrations. And this scaffold dictates where electrons are allowed to be, where they're allowed to move, and just as importantly, where they are forbidden. This is really the whole foundation of quantum band theory. Electrons can't just have any energy they want. They have to live in these allowed energy bands. That constraint is what makes reliable computation even possible.
And those bands are separated by that crucial bit of forbidden territory, the band gap, EG. For something like silicon or germanium, that gap is around 1 electron volt. It's the energy hurdle that keeps the entire system from just dissolving into chaos.
Precisely. The stability of that gap is absolutely everything. If EG were too small, thermal entropy, Ceph just heat, would constantly be kicking electrons across the gap. The semiconductor would become an unstable conductor, no reliable switching.
Right, it would just be noise.
Just noise, but if EG were too large, it would be an insulator. And no amount of voltage could really create the flow you need.
So the band gap isn't just a physical property, it's an engineered barrier. It's specifically designed to separate states. You have the valence band, nearly full of electrons, and then the conduction band, which is nearly empty. The carriers, then, are the structural motion components we actually get to manipulate. The mobile electrons in the conduction band and
the holes.
And the holes, right, the sort of conceptual missing electrons in the valence band.
And this is where Shockley realized the true power was. It was in doping. Doping, adding impurity atoms into the crystal, is the physical act of permanently altering the local motion balance. It doesn't just add charge. It fundamentally changes the energy landscape. It defines how easily certain structured motion patterns, the carriers, can actually propagate. You are physically engineering the on-ramps and off-ramps for this energy highway.
That makes perfect sense. So instead of just thinking of N-type and P-type as just, having negative or positive carriers, we should see them as predefined pathways for negative and positive structural energy flows.
It's all about stability. Doping ensures that even when everything's at thermal equilibrium, you have a stable excess of one carrier type. And that stable starting condition was exactly what Shockley needed to build his first motion gate.
Which brings us right to it, that foundational motion gate.
Mm.
the PN junction, the diode. So you
Mm.
join P-type material, which is rich in holes, and N-type material rich in electrons. Diffusion happens, and that diffusion creates this internal fixed energy barrier. This is the definition of a one-way motion gate. Now, when Shockley modeled the current flow, I, versus the applied voltage, V, he derived the famous diode equation. And in that equation, there's that exponential term, e to the QV over kBt. To me, that looks like pure statistical mechanics, maybe chemistry. How does motion theory make that specific equation clearer? Or more useful than just the standard Boltzmann view?
That's an excellent question, because you're right, the math is the math, whatever framework you use. But MT provides the physical meaning of that exponential. It frames it as a competition between entropic forces. The Boltzmann distribution usually just describes the probability of a particle having enough energy to get over a barrier.
Hmm.
In MT, that exponential describes the probability that the random thermally driven motion, the C of a carrier, is sufficient to win against the built-in energy barrier and create a measurable, directed current flow, a signal, and scope.
Oh, okay.
So the denominator in that term, kBt, that's the thermal energy. That's the source of all the random motion. The numerator, QV, is the directed energy you're supplying with the external voltage. So you are literally measuring the ratio of the directed energy flow your signal, trying to overcome the constant random thermal agitation that wants to keep the system perfectly balanced.
So the diode, at equilibrium with no voltage, is a perfect balance. There's tons of motion going on, but the random flows of Stith from both sides just cancel each other out.
Yeah.
Zero net current, no structured signal.
Correct. The internal barrier is set perfectly to keep the system stable and quiet.
Okay, so let's apply an external voltage, a forward bias. What happens to the flow then?
Forward bias is how we inject structured motion. Applying that voltage, it actively reduces the internal potential barrier. And when that barrier gets lower, the probability of SCO, that directed carrier movement, winning the competition and crossing the junction just skyrockets exponentially. And that's your massive current flow. You've created an easy path for structured movement.
And backward bias is the opposite.
Backward bias is the hard no. You raise that potential barrier, you make it much, much higher. Now, only the most energetic, the rarest random thermal events, these extreme sloth occurrences, can manage to jump that enormous barrier, which results in just a tiny, insignificant leakage current. The gate is firmly closed to any structured signal flow.
So the ability to create a reliable own-FF switch was, that alone was transformative. But the real leap, the invention that truly powered the entire information age, was the move from the two-terminal diode to the three-terminal transistor.
Absolutely. The diode controls flow based on the height of the barrier. Shockley's critical move, and this is what led to the bipolar junction transistor, the BJT was figuring out how to control the flow not just by barrier height, but by influencing the carrier density and lifetime in a crucial middle region. He used one small region, the base, to control a massive flow between two other regions.
Okay, let's talk about the architecture of this motion valve. We have the emitter, heavily doped. It acts as the injection point for the carriers. Then the collector, which grabs them on the other side. And then there's the base, that incredibly thin, lightly doped layer sandwiched right in the middle.
And the thickness of that base is the core physical innovation. It defines the performance, it defines the gain. Early on, Shockley had struggled with the field effect transistor, the EQT. He was trying to control current by applying a voltage near the surface. He and his team realized they needed to get inside the material to penetrate the surface, and that led to the BJT invention that his colleagues Bardeen and Brodin first built. But it was Shockley who gave them the deep theory on how the junction geometry had to work.
So how does that incredibly thin base actually create amplification?
Well, think of the emitter like a fire hose. It's injecting a high density of carriers into that base region. Now, the structured motion of those carriers has two choices. It can flow out the base terminal as a small control current, or it can continue diffusing across that thin base region towards the collector.
And because the base is so thin...
Exactly. Because the base is designed to be physically very thin, we're talking much smaller than the diffusion length or recombination lifetime of the carriers. Most of them survive the trip. They survive their journey across the base without being annihilated by Stith, by recombination. They maintain their structural integrity just long enough to reach the collector junction.
So the thinness is what prevents the signal structured pattern from being, as you say, eaten by stuff before it can get across.
Precisely. A tiny control current, or even just a voltage tweak at the base, changes the internal potential slightly, and that diverts a small fraction of the carriers. But because the vast majority of that emitter current survives the crossing, the collector current becomes this huge multiple of the tiny base control current. That ratio is the current gain, beta. You're talking about a tiny, precise input of scope successfully channeling a flow that's hundreds of times larger. It's the ultimate motion amplifier.
And that explains why these devices have to operate in a constant non-equilibrium state. We're always actively driving carriers into that base region, creating these temporary, highly structured patterns of electrons and holes.
And that non-equilibrium state forces us to deal with time. Shockley's comprehensive theoretical work was all about defining these crucial timescales. You have drift time, which is how fast carriers move under a field, diffusion time, how fast they move randomly, and the critical one, recombination lifetime.
The recombination lifetime. So, viewed through MT, that's basically the clock counting down until the signal's structured motion pattern gets erased. It's when SCO gets overwhelmed by the random thermal noise, seeth. It's the literal lifespan of a reliable digital signal.
That is the race. That's the whole game. Shockley taught engineers how to design devices where the structural integrity of the signal survives just long enough to perform a logical task, like a switch, but also dies quickly enough so the device can reset and reliably perform the next task millions of times per second.
And when you scale that reliable on-off motion dial into the billions, you build the digital universe. Logic states, 0 and 1, they stop being abstract concepts and they become tangible physical realities. There's simply two stable engineered motion regimes in the circuit. Low current or low voltage is your logic 0, and high current or high voltage is your logic 1.
And a computer is simply a meticulously choreographed, synchronized dance of these motion loops. The physical constraints we engineer into the silicon, the doping, the geometry, the voltage biases, they turn raw carrier motion into what we perceive as long-lived symbolic motion. It's the physical realization of that wonderful phrase, logic is just motion with very strict manners.
And while it was Shockley's peers and successors who built the first integrated circuits and the microprocessors, he's the one who provided the underlying physics. The reliable blueprint for switching motion that allowed everyone else to scale this pattern into the billions of devices that run modern life.
And it's impossible to discuss this scale of technological power without addressing the man himself. We've focused on the foundational physics, which is objective, it's verifiable, but we have to acknowledge that his legacy is complex and deeply troubled.
He had a huge role in creating the early culture of innovation in what became Silicon Valley. He famously sparred with the traitorous 8, who left him to found Fairchild Semiconductor. But later in his life, he became notorious for promoting pseudoscientific, racist, and eugenics-based ideas about human intelligence.
It represents a profound moral failure. It's a stark reminder that the brilliance it takes to unlock the physical laws of the universe doesn't automatically grant you any moral authority or, frankly, good judgment when it comes to human organization.
And we have to maintain that intellectual separation. The physics he revealed, how to organize energy flow in a crystal that is neutral. It is simply a powerful set of physical tools. But the decisions about how to wield that power, whether you use it to build enabling technologies or to structure harmful societal hierarchies, those decisions are entirely separate from the material science. The technology is just a container for structured motion. The intention we pour into that container is on us.
So to summarize Shockley's ultimate contribution, he taught the world how to organize electron patterns so that a small, structured control could exponentially reshape a much larger energy flow. As we've said, he engineered matter so that a transistor is a crystal that learned how to say yes or no to motion.
Now, for our final thought, let's turn to the physical limits this motion control imposes on us. Our sources talk about MT predictions for the ultimate maximum speed of computing, specifically the synchronization limit on clock speed P3. How does the MT framework use this idea of coherence to define the absolute limit of speed?
The standard view is often about heat, right? Or how quickly electrons can drift. MT suggests the failure mode is actually structural. If you push a processor, say a ring oscillator, faster and faster, MT predicts the device fails when the coherence length of the carrier motion inside the switch falls below the size of the physical switch region itself.
Wait, I need to visualize that. So the signal's structured pattern, it literally loses its structural integrity before it can successfully cross the base or flip the switch. It just becomes random with mid-operation.
Precisely. If your clock speed is too high, you are demanding that the structured pattern of carriers propagate across the physical distance of the transistor faster than the laws of physics, allow that structure to be reliably maintained. The structural information dies before it finishes its journey. The switch fails. It can't reliably tell the difference between a 0 and a 1 anymore.
Wow. That completely shifts the engineering challenge. It suggests the ultimate speed limit of computing isn't just about making things smaller, but about how long we can actively sustain that required coherent structure, the SCO, before the inevitable thermal noise, the scoth, just overwhelms it.
It's a perpetual battle against entropy. And understanding that we are, at a really fundamental level, just engineering the lifespan of structured motion patterns inside silicon. That is Shockley's lasting and, I think, profound insight. What we choose to build with these billions upon billions of microscopic motion valves, well, that's a question that remains open.
A fascinating insight to leave us with. Thank you for guiding us through this deep dive.
My pleasure.